So the CMOS logic family seems to have a lot of advantages, and this is the time to make an account of these advantages, but more importantly, it is also a time to account for the price that we pay for these advantages. So understanding what's good about CMOS is always easier to do when we consider it in comparison to ratioed logic families. So ratioed logic families look like this. There was a driver and there was some kind of load. For gates, we had a pull-down network and there was still the same load, and the output was taken and under the load in all cases. For CMOS, we had no driver and no load. In fact, both transistors played the role of a driver, and their input was provided to an NMOS and a PMOS transistor. In gates, we have a pull-up network that consists of n PMOS networks, of n PMOS transistors, and a pull-down network that consists of n NMOS transistors. The output is taken in between the two networks. Each network has the same number of inputs provided to it, and the same inputs exactly, actually. So if we compare the two, we find that CMOS logic has four main advantages. The first is that V output high is equal to VDD, and V output low is equal to 0 volt. So it increases the distance between clean 0 and clean 1 to the maximum possible. Secondly, that neither V output high nor V output low are functions of transistor sizes. So neither output values are functions of transistor sizes. V output in the steady state in both cases is independent from transistor sizes. The third thing is that static current was always 0. Steady state current was always 0. And the fourth thing is we had a tight transition region in the VTC. So at least three of these work together so that we have a good noise margin for CMOS. The first, second, and fourth facts give us the maximum amount of noise margins that we can get from any realistic logic family. So V output high is at VDD, V output low is at 0 volts, so they give us the maximum and there's no headroom lost on either side. Also, V input high is a relatively low value, V input low is a relatively high value, and Vm is a single value for which both transistors are saturated, giving us a relatively narrow transition region, which means that noise margin high and noise margin low are going to be relatively high, like this. Of course, we talked about how the transition region is going to be made wider, and thus the noise margins are going to lose some if we take into consideration the channel length modulation effect. But still, CMOS is the most robust logic family you can think of. It has the best noise margins available. So why is CMOS capable of doing this? The main thing about CMOS is that there is zero steady state current. This is the main thing that makes it work. And because there's zero steady state current, there's always a path that shorts the output node to either supply or to ground. So what happens is we always have an open circuit created to either ground or supply in either the PDN or the pull-up network. When we have an open circuit in either network, there will be a path to supply or ground in the other network. And so when we have that path and we have an open circuit in the opposite network, we have zero steady state current. The zero steady state current causes zero drop on either the pull-up or the pull-down path, shorting the output to either 0 volt or to supply, independent of transistor sizes. So what causes this to happen? What causes the complement network to open a path while the other network shuts all paths? This happens because we have complementary connections in the two networks. So if we have a connection that opens in the pull-up network, we'll have a similar connection that shuts everything down in the pull-down network. And we discussed all of this in detail. But now it's time to talk about something different, which is what are the disadvantages of CMOS. And again, when we discuss disadvantages, we have to discuss them relative to a ratioed logic family. So a really good way to look at the disadvantages is to consider a two-input NOR gate in both regimes. So let's look at an enhancement load two-input NOR, and it has, actually let's make it a three-input NOR, because this is going to make it even more clear. So we have an input A, and let's consider this input A in the enhancement load NOR. And let's also consider a CMOS 3-input NOR, so the same gate doing the exact same function, except with all the advantages we talked about, right? And then there's A here, and then A, B, C in the pull-up network. And we want to find out how the CMOS network, this network, is inferior to this enhancement load network. We know all the ways that the CMOS network is superior to it, but how is it inferior? First of all, there is area, or more specifically, the number of transistors. If we compare the number of transistors, there are 6 transistors here, and there are 4 transistors here. And by induction, we can extend this to any kind of network with n inputs. The CMOS network is going to have 2n transistors, and the ratioed family is going to have n plus 1 transistors. The n comes from the PDN, and the 1 is the load. Here, the 2n, one of them, 1n goes to the PDN, and 1n goes to the pull-up network. So we can say that the CMOS network is going to roughly have double the area of the comparable ratioed logic family. But in fact, it's even worse than that, because half of the network, half of the transistors in the CMOS network are PMOSs. And PMOSs, as we saw, usually need to be sized larger than their NMOS counterparts in order to account for the lower mobility. So it's even worse than double the area. It's more than double the area, because the PMOS transistors are going to be much bigger than their NMOS counterparts. So this is one disadvantage. And actually, this is the more minor disadvantage. Even though it might look really severe, this is the more minor disadvantage. The more major disadvantage we can see here, if you look here, this gate provides a loading to the gate before it through both the NMOS transistor and the PMOS transistor. And this gate itself is going to also see inputs coming from a next CMOS gate. It could be an inverter, it could be anything else. And we are going to see loading coming from CGN and CGP. Whereas the ratioed family gate is going to see loading from a single transistor, only an NMOS. So this is going to see CGN. So basically CG in this case is almost double CG in this case. In fact, it's even worse than that, because CG is going to be NMOS loading and PMOS loading. And PMOS loading is not going to be equal to the NMOS loading. It's going to be larger, because we need to size the PMOS transistors larger than the NMOS transistors to account for mobility. So gate loading is going to be more than double. And this means that delay for CMOS is going to actually be more than double than delay for a ratioed logic family. In fact, it's even worse than that. It's much, much worse, because the fact that we have given the input to both the NMOS and the PMOS transistor in CMOS, the fact that we have provided an input to both transistors at the same time, means that there is a strong susceptibility to the slope of the input voltage. We discussed this in detail when we discussed short circuit current. There is a period of time where both the NMOS and the PMOS are on, which means that there's a period where there's a short circuit current flowing that does not contribute to charging or discharging the capacitance. Whereas in the ratioed logic family, the input is provided only to the NMOS. There's no PMOS. And therefore, when we shut down the NMOS, there's nothing that counteracts it on the top. In fact, the load is going to shut down. It's not going to counteract the driver the same way the PMOS does in the CMOS network. And so when we think about the CMOS logic family, it's basically a trade-off between robustness and delay. Area is a secondary factor. What really matters is that we are getting robust operation with large noise margins, and yet we are paying the price in terms of delay by having to deal with more than double the delay. If we say it's double the delay, we are assuming that the PMOS transistor that we see at our output is sized similar to the NMOS network, which is rarely the case. So we have to deal with much worse delay. And this sets up the stage for dynamic gates, which actually address all of the problems we have with CMOS while preserving the advantages of CMOS.